Welcome to a lesson with Dr. Powell. Let's talk about what it means to prove something by induction. Essentially, we have some kind of statement or a proposition, and if we can form a chain of implications that follow a path like this and just keeps on going. If you thought of this as like a Hasse diagram or a post set or something, what would happen if you took the meat or the intersection of all these guys? You'd simply just get that guy at the beginning. So the statement of ands, which is like intersection of all of these guys, that all of these true are the same thing, are at the same time, is precisely the first statement. They're logically equivalent if you can make this chain. So if you can make a chain and then you can prove that this guy is true, then you've just proved that all of them are true, all together at the exact same time. So, okay, so here's a little example of such a proof by induction. Let's suppose that we have the statement right here that n factorial is less than or equal to n to the n. And actually, this is lots of statements. It's a statement for every single n. And let's suppose we just take n that are counting numbers. And we want to show that all those statements are true. So starting at 1 and going on. So let's suppose that n, little n, is in big N. Okay. All right. So each one of these is a statement. Well, first of all, let's look at the first statement, A1. Is that true? Well, clearly, let's go with the statement. 1 factorial is less than or equal to 1 to the 1. Yes, that's true. Okay, so A sub 1 is true. Now, let's just show in general that we have this implication chain. To show we have an implication chain, we only need to establish a generic arrow. A sub n implies A sub n plus 1. We need to actually show this. So that means we need to assume this and show that that assumption implies that this would be true. So the truth of this implies the truth of that. Okay, so, well, let's begin. Let's just assume then that this statement right here, A sub n, is true. Assume it's true. Great. Now, let's take a look at this one. N plus 1 factorial is less than or equal to n plus 1 to the n plus 1. So we want to get here by first using this guy. Okay, so maybe we'll just start thinking about this. Let's just start on the left side and see if eventually we can get over to this side to be in an inequality using this part. So where is n factorial inside of n plus 1 factorial? Well, we can think of n plus 1 factorial as actually being just simply n plus 1 times n factorial. There it is. Then we put a less than or equal to, and then think about this. Let's just use this thing right here. This n factorial is less than n to the n. And we've just multiplied this by n plus 1 on both sides, you could say. That's kind of nice. And this is equal to n plus 1 factorial. And we already know, oh, that's an n to the n's, excuse me, n to the n. Okay, and we already know that's less than or equal to n plus 1 times n to the n. Now, we also know a couple other things. We know that n is less than n plus 1, naturally, because n plus 1 is 1 more. So we could actually, in this inequality, say n plus 1 times n plus 1 to the n. Then look at these exponents. They add n plus 1 to the n plus 1. Whew, we just showed that this was less than this. And along the way, we used an assumption. This is called the inductive hypothesis, or the inductive assumption that we used to move from here to here. And then we're done completely with the proof. So we've just proved an infinite number of statements all in one go, just by doing two things, proving that the beginning of the chain is true and proving that the chain exists. Thanks for watching.